Hi students, as you know, NDA has introduced a new unit in the chemistry syllabus for both the NEET and JEE from the year 2024 onwards. The new unit included is the principles related to practical chemistry. Since it is a newly introduced topic, the necessary study materials may not be available in print and visual media. But you need not worry. I am uploading video classes through my YouTube channel explaining the theory related to chemistry practical, which include a lot of multiple choice questions and their well explained answers. By the way, I am Dr. Siriak Matthew, a retired associate professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to topics in chemistry within secondary, undergraduate, and postgraduate levels. At present, I am uploading video classes related to NEET, JEE Main and Advanced, and other entrance examinations. There will be a set of video classes for each chapter. In the present set of videos, we discuss the principles related to practical chemistry. This set includes 6 video classes. The first one, titled as Principles Related to Practical Chemistry, Part 1A, explained detection of extra elements and detection of functional groups. The second, titled as Principles Related to Practical Chemistry, Part 1B, contains multiple choice questions related to Part 1A. Part 2 explains preparation of some organic and inorganic compounds and a titrimetric analysis. Part 3, qualitative analysis for anions, and Part 4, qualitative analysis for cations. The Part 5 explains some physical chemistry experiments. At the end of each part, multiple choice questions related to that part are explained. Even if you go through a handbook of chemistry practical several times, you may not be able to remember the experiments and the theory behind it. But an audiovisual presentation will catch your attention. That is why I have introduced a lot of animations in these video classes so that you will get a feel of doing the experiments in the laboratory. However, animations never represent the real situation. And this is not an instruction manual for doing the experiments in the lab. The main purpose is to make you understand the theory behind the experiments. In the laboratory, you have to take several precautionary measures while doing the experiments. For your convenience, I have introduced video chapters or timestamps in the description part of the videos. This will help you to watch and rewatch separately the different topics explained in a particular video. The links for other videos are also given in the description part. You can easily move to any of these 6 videos using these links. I hope these video classes will definitely help you to understand the theory behind the experiments. If you like the video, please subscribe my channel and forward to others. You can expect similar video classes from other chapters of Class 11 and Class 12 Chemistry soon. In this video, we study about the theory behind some physical chemistry experiments. The first experiment we study is the determination of enthalpy of solution of copper sulphate. Like chemical changes, physical changes are also associated with enthalpy changes. Most of the chemical and physical changes we carry out are atmospheric pressure. Therefore, we consider the heat changes as enthalpy changes delta H. The enthalpy of solution is defined as the amount of heat liberated or absorbed when 1 mole of a solute, either solid or a liquid, is dissolved in such a large quantity of solvent, usually water, that further dilution does not make any heat changes. When a large quantity of solvent is used, the solution will be very dilute. In dilute solutions, the interaction between ions or solute molecules are negligible. We know delta H is equal to Qp, where Qp is the quantity of heat exchanged at constant pressure. Qp is equal to mCp delta T. where M is the mass, Cp is the heat capacity, and delta T is the change in temperature. You have studied this relation in thermodynamics. Qp, we can also write it as Qp is equal to V d Cp delta T, where V is the volume of the solution and d is the density of the solution. Now let us see how we can measure the enthalpy changes. Heat changes are measured using a device called calorimeter. In a laboratory, we can use a well-insulated glass beaker for measuring heat changes. Generally, metallic calorimeters are not used for measuring thermochemical changes because metals may react with the substances. Stainless steel or gold-plated copper calorimeters can be used. For approximate laboratory measurements, even a styrofoam cup can be used. We can use conveniently a 250 ml beaker placed in a 500 ml beaker as a calorimeter. In between these two, we pack cotton wool to prevent heat loss. So this is a 500 ml beaker. We pack it with the cotton wool. In the middle of that, we place the 250 ml beaker. Then we place a thermometer for measuring the temperature changes and a glass stirrer for mixing the solution. We close the beaker using a wooden disc to minimize heat loss. The wooden disc can be easily moved up and down. During the measurement of heat changes, the calorimeter, thermometer, and a stirrer also absorb some heat, and it is called the calorimeter constant. We must know this amount of heat. In the case of glass vessel, such as a beaker, we need consider only that part of the vessel which is in contact with the reaction mixture. This is because the thermal conductivity of glass is low and only the area of the calorimeter in contact with the liquid absorbs maximum heat. To determine the calorimeter constant, we use the method of mixtures. A known volume of hot water at a specified temperature is added to a known volume of water contained in the calorimeter at a room temperature. First, let us set up the calorimeter, the larger beaker, pack it with cotton wool. Now place the smaller beaker in it. And I have placed about 100 ml water at a room temperature, a glass stirrer and thermometer. And now I close the calorimeter using the wooden disc. And I note down the temperature of water taken, let it be Tc. Now lift the disc and take a known volume of hot water. Suppose the temperature is Th, and I quickly transfer it into the calorimeter. Now close the disc, stir the mixture well by moving the stirrer up and down, and note down the maximum temperature attained. So let it be Tm. Temperature of cold water equal Tc. Temperature of hot water is Th. Maximum temperature attained is Tm. Therefore, delta T is equal to Tm minus Tc. Since energy is conserved, the heat taken by cold water, thermometer, stirrer and calorimeter must be equal to the heat lost by the hot water. Therefore, we write delta H1 plus delta H2 is equal to minus delta H3, where delta H1 is the enthalpy change or heat change for calorimeter, stirrer and thermometer. Delta H2 is the enthalpy change of cold water. Delta H3 is the enthalpy change of hot water. And delta H3 is negative because heat is lost by the hot water. Let us calculate the calorimeter constant from the data we obtained from the experiment. The heat absorbed by calorimeter, thermometer and a stirrer is called calorimeter constant W. Delta H1 is the enthalpy change for calorimeter, thermometer and a stirrer. Delta H2 is the enthalpy change for cold water. Delta H3 is the enthalpy change for hot water. And now we have already seen this equation, delta H1 plus delta H2 is equal to minus delta H3. Let Cp1 be the heat capacity of calorimeter, Cp the heat capacity of water, M mass of calorimeter, and Mc mass of cold water, Mh mass of hot water. And for convenience, we take the density of water as 1 gram per ml. Heat gained by calorimeter will be mass of the calorimeter into heat capacity of calorimeter into the temperature difference. And this quantity we take as W, that is the calorimeter constant. So W into Tm minus Tc. Heat gained by cold water, that is mass of cold water into heat capacity of cold water into difference in temperature. Heat lost by cold water, we take it as negative. Heat capacity of mass of hot water, heat capacity of water, and temperature difference. Now, the heat gained by calorimeter and heat gained by cold water is equal to heat lost by the hot water, or W into Tm minus Tc is equal to, we isolate this quantity, that is minus mass of hot water into Cp, temperature difference, minus mass of cold water into temperature difference. So from this we get W as minus Mh Cp Tm minus Th minus Mc Cp Tm minus Tc by Tm minus Tc. Tm is the maximum temperature attained, Tc is the temperature of the cold water. And here Tm is the maximum temperature attained and Th is the temperature of hot water. Tm is less than Th. Now, W is equal to, we take Cp of water outside and Cp into Mh into Tm minus Th plus Mc into Tm minus Tc by Tm minus Tc. The heat capacity of water, Cp, is the amount of energy needed to raise the temperature of 1 gram of water by 1 Kelvin or 1 degree Celsius. And this quantity is 4.184 joule. Therefore, we multiply this equation by 4.184 joule. We get the calorimeter constant in joule per Kelvin. And this quantity will be positive because Tm minus Th is negative, because maximum temperature attained is less than the temperature of hot water. Now let us determine the enthalpy of dissolution of anhydrous copper sulphate. In thermochemical measurements, generally aqueous solutions are mixed. From the law of conservation of energy, sum of enthalpy changes taking place in the calorimeter must be 0. There occurs loss and gain of energy. Dissolution of a salt in a solvent is always accompanied by heat changes. Enthalpy of solution is the amount of heat liberated or absorbed when 1 mole of a solute, solid or liquid, is dissolved in such a large quantity of solvent, usually water, that further dilution does not make any heat changes. First, we determine the calorimeter constant according to the method discussed earlier. So I have taken the calorimeter and it is closed with its lid, and 100 ml water is taken inside the calorimeter. I have placed a thermometer and stirrer also. Note down the temperature of water taken. Let it be T1 degrees Celsius. Now lift the lid and take some anhydrous copper sulphate and let it be W1 gram and quickly transfer it into the calorimeter and close the lid of the calorimeter. And now thoroughly mix the solution by moving the stirrer up and down. The temperature rises and note down the maximum temperature attained. Now let us do the calculation. Mass of water 100 gram. We take the density as 1 gram per ml. Mass of copper sulphate W1 gram. Temperature of water T1 degrees Celsius. Maximum temperature attained T2 degrees Celsius. Total mass of solution 100 is the mass of water. W1 mass of copper sulphate. Change in temperature, that is T2 dash minus T1 dash degrees Celsius. Calorimeter constant, we have determined it earlier, W. Enthalpy change for calorimeter, W into change in temperature. Enthalpy change for the solution, total mass into temperature change. Now the total enthalpy change equals W into T2 minus T1 plus 100 plus W1 into T2 minus T1 into 4.184 heat capacity of water. Heat liberated for 1 gram copper sulphate, that is this quantity divided by mass of copper sulphate. 1 mole of anhydrous copper sulphate base 159.5 gram. Therefore, enthalpy of dissolution of anhydrous copper sulphate, we multiply this quantity by, that is for 1 gram, and multiply by 159.5, we get the enthalpy of dissolution of anhydrous copper sulphate in joule per mole. In the laboratory, we use hydrated copper sulphate for convenience. Anhydrous copper sulphate is highly hygroscopic. The enthalpy of solution is positive for copper sulphate 5:2. Molar mass is 249.5 gram per mole. Heat will be absorbed during the dissolution. So for hydrated copper sulphate, heat will be absorbed during the dissolution process. When an ionic compound dissolves in water, the ions leave the ordered position of the crystal lattice and become free. Energy is needed for this process, and if it is taken from the surroundings, so the process is endothermic. This happens generally with compounds which do not form hydrates and hydrated salts. But when an anhydrous salt is dissolved in water, hydration occurs, which is an exothermic process, and releases more energy than that needed to dissolve the salt. Hence, the process is exothermic. Next, we determine the enthalpy of neutralization of a strong acid and a strong base. A neutralization reaction involves the combination of H plus ions produced by an acid and OH minus ion produced by a base to form liquid water. Neutralizations are always exothermic since bond formation occurs during the reaction. Enthalpy of neutralization is the amount of heat liberated when 1 mole of H plus ion supplied by acid combined with 1 mole of OH minus ion supplied by base to form water. It is represented as delta neutralization H and is negative always. So H plus ion from the acid, OH minus ion from the base, we get H2O liquid. Enthalpy of neutralization of a strong acid against strong base is always a constant. It is 57 kilojoules per mole. This is because in any strong acid strong base neutralization, the net reaction is the formation of 1 mole of liquid water by combination of 1 mole of H plus and 1 mole of OH minus ions. If any one of the acid or base or both are weak, some amount of heat liberated will be used for the ionization of the weak acid or base. Then the amount of heat liberated will be less than 57 kilojoules per mole. For doing the experiment, we need the following solutions. 100 ml acid of concentration 1 molar. Base also is 100 ml. Molarity of base also is taken as 1 molar. So I have taken 1 molar HCl 100 ml in the calorimeter. Now close the lid and note down the temperature. Let it be T1. Now take 1 molar NaOH 100 ml in a beaker and its temperature also will be the same. Now lift the disc and quickly transfer the sodium hydroxide into the calorimeter. Now close the disc and stir the mixture well using the stirrer. The temperature rises and note down the maximum temperature attained. Let it be T2. So the difference in temperature delta T is equal to T2 minus T. Next we will do the calculation. Temperature of acid T1, temperature of base T1, temperature of solution is T2. Rise in temperature is T2 minus T1. The calorimeter constant W, this is a known quantity. Therefore, heat evolved during neutralization, 100 volume of acid, volume of base, and this is the calorimeter constant into temperature difference. And when we multiply it by 4.184 joules, we get the value in joule. Equation 1 gives the heat evolved when 100 ml 1 molar HCl is neutralized by 100 ml 1 molar NaOH. Therefore, for neutralization of 1000 ml or 1 liter 1 molar acid and 1000 ml 1 molar base is obtained by multiplying the above quantity by 10. We multiply this quantity. This is for 100 ml. So we multiply by 10. Then you will get the heat evolved for 1000 ml. So enthalpy of neutralization is 100 plus 100 into 4.184 into 10 kilojoules per mole. The next topic we have to study is colloids. And we know that solutions are homogeneous systems. When fine sand is mixed with the water and stirred, form a suspension, and which slowly settle down with the time. Between these two systems exists another system which is called colloidal system or simply colloids. A colloidal system is a heterogeneous system in which very fine particles of one substance dispersed in another substance called dispersion medium. Dispersion medium. The substance which is dispersed is called dispersed phase. Dispersed phase. Dispersed phase and dispersed medium together is called colloidal sol or simply sol. So dispersion medium, dispersed phase, together they form a colloidal sol. And let this be a colloidal sol. And we cannot see the particles with our naked eye. Suppose that I enlarge a small portion. And this part is the dispersion medium, the medium in which the particles are dispersed. And these are the colloidal particles. The size of the particle vary between 10 raised to minus 9 to 10 raised to minus 6 meter. The essential difference between a solution and a colloid is the particle size. In solution, the constant particles are ions or small molecules. On the other hand, in a colloid, the dispersed phase may consist of particles of single macromolecules such as protein, starch, etc., or aggregates of many atoms, ions or molecules. An example for that is colloidal sulfur. Colloidal particles are larger than molecules but small enough to remain suspended in dispersion medium. It will not settle down. The size vary between 10 raised to minus 9 to 10 raised to minus 6 meter. Types of colloids. Depending on the nature of the interaction between dispersed phase and dispersion medium, two types of colloids exist. One is called a lyophilic colloid, that means solvent attracting. And the second one is lyophobic colloids, that is solvent repelling. If water is the dispersion medium, the term used are hydrophilic colloids, for example egg albumin, starch, gum, etc. Hydrophobic colloids, for example, freshly prepared ferric hydroxide, aluminum hydroxide, arsenic sulphide, etc. The particles of dispersed phase in lyophilic salts have an affinity for the particles of the dispersion medium, hence stable compared to lyophobic salts. Now, two factors are responsible for the stability of salts. One is the charge on the surface of the colloidal particle, and the second one is the solvation of the colloidal particle by solvent. Stability of lyophilic salts is mainly due to the solvation of colloidal particles by the solvent molecules. Lyophobic colloids are stabilized by charge on the colloidal particles. Because of the charge, the colloidal particles remain suspended in solution. Coagulation does not occur. The charge present may be either positive or negative. Some examples of negatively charged salts are starch, arsenic sulphide, gold salt, etc. Some positively charged salts are hydrated ferric acid, Fe2O3 titanium dioxide, salt, etc. The process of settling colloidal particles is called coagulation or precipitation of salt. The lyophilic salts are directly formed by mixing and shaking the substance with a suitable liquid. Lyophobic salts cannot be prepared by direct mixing or shaking. So therefore, special methods are needed to prepare lyophobic salts. And this is an example of a salt, and it is a negatively charged salt. For example, starch. And this is another example, and it is a positively charged salt. And for example, hydrated ferric acid, etc. Now let us discuss the preparation of some lyophilic salts. And first we consider the preparation of egg albumin salt. We take an egg and a small hole is made in it. Carefully pour the albumin into a porcelain dish. This is egg albumin, that is white. Now we take about 5% sodium chloride solution in water. Prepare 5% sodium chloride solution in water. And carefully pipette out some of the albumin and transfer it into the 5% sodium chloride solution. And stir the mixture well. And we get egg albumin salt. So this is egg albumin salt. Now we prepare a starch salt. And first we take some distilled water and heat it. And make a paste of 500 milligram of starch in hot water and transfer it to 100 ml boiling water with a stirring. So we are transferring it to the beaker, and using a mechanical stirrer we are stirring it. So the starch salt is produced. This is starch salt. Under kinetics we study the effect of variation of concentration of iodide ions on the rate of reaction of iodide ions with hydrogen peroxide at a room temperature. Before going to the details of the experiment, we will discuss some of the main points of chemical kinetics, and you have studied all these under chemical kinetics chapter. Chemical kinetics studies about the rate or speed of a reaction. Rate of a reaction is the change in concentration of any one of the reactants or products in unit time. Generally, the rate of a reaction is found to be not the same throughout the reaction. It is found to be maximum in the beginning, that is initial rate, and decreases as the reaction proceeds. Therefore, we consider average rate as well as instantaneous rate. The average rate is the ratio between total change in concentration and the total time taken for that change. And as a general example, we take the reaction R giving P, where R is the reactant and P is the product. Suppose we plot the concentration of reactant against time, we will get a graph like this. So X1 is the initial concentration of the reactant, X1 is the initial concentration of the reactant at a time T1, and X2 is the concentration of the reactant at a time T2. So therefore the average rate will be X2 minus X1 divided by T2 minus T1. And since X2 is less than X1, so we put a negative sign here. So therefore the average rate is equal to minus delta R by delta T, and the negative sign shows that the concentration of reactant go on decreasing during the reaction. The unit of rate is mole per liter per second. Based on product also we can express average rate, that is change in concentration of product by change in time. Instantaneous rate is the rate of a reaction at an instant and is represented as the derivative of concentration with respect to time. So instantaneous rate is equal to dx by dt, where x is the concentration. Based on the reactant, it is minus dr by dt or dp by dt. The rate law equation. For common reactions, rate depends on the concentration of the reactants. For the reaction A moles of A plus B moles of B giving products, the rate could be written as rate is equal to K into A raised to X, B raised to Y, where this term represents the concentration of A and concentration of B. Concentration of reactants in mole per liter or partial pressure. X is the partial order with respect to A, Y is the partial order with respect to B, and the overall order of the reaction N is X plus Y. The K here is the rate constant. It is a constant for a given reaction under a given set of conditions. Another term we have to learn is order. Order shows how the concentration of the reactants affect the rate of a reaction. Based on order, we classify reactions into 0, first, second, etc. order reactions. Reactions with the fractional order are also there. Another is molecularity. It is the number of reactant species which collide simultaneously in an elementary reaction, leading to formation of products. It is applicable to elementary reactions only. Elementary reactions are those reactions which take place in a single step. Three main factors that affect the rate of a reaction are concentration of the reactants, temperature, and the presence of catalyst. Other factors are also there. Let us come to the experiment, that is the kinetic study of reaction between iodide ions and hydrogen peroxide. And this reaction is also known as the cloak reaction. Our aim is to study the effect of variation of concentration of iodide ions on the rate of the reaction between iodide ions and hydrogen peroxide at room temperature. And the reaction takes place in acid medium. This is the reaction, the iodide ion plus hydrogen peroxide, acid medium, we get molecular iodine. The hydrogen peroxide oxidizes iodide ions to iodine. In order to follow this reaction, we use a second reaction along with the first one. And we know that sodium thiosulfate will react with iodine and converts it back to iodide ions. So iodine plus sodium thiosulfate, and it is converted to iodide ion, and thiosulfate is converted to the tetrathionate. We add calculated amount of sodium thiosulfate and some starch solution to the above reaction mixture. Hydrogen peroxide oxidizes iodide to iodine, and iodine produced react with the sodium thiosulfate as fast as it is formed. Thiosulfate reduces it back to iodide ions. When all the thiosulfate ions are consumed, the iodine produced remain in solution and forms I3 minus ions. These ions combine with the starch and shows a blue color. The appearance of blue color indicates that the thiosulfate has been completely reacted, and we note down the time required for that. We repeat the experiment with the same amount of thiosulfate but different concentration of iodide ions every time, noting the time required for the appearance of blue color. Since we follow the reaction by noting down the time for color change to occur, the reaction is also called cloak reaction. We should always keep the concentration of sodium thiosulfate solution less than that of the potassium iodide solution used. These are the solutions we need for doing the experiment. Sulfuric acid 2.5 molar, iodine peroxide 3%, potassium iodide 0.1 molar, sodium thiosulfate 0.04 molar. The concentration of sodium thiosulfate is much lower than that of the concentration of potassium iodide. Distilled water and a starch solution. We take a conical flask labeled A, and to that we are adding iodine peroxide 25 ml, sulfuric acid 25 ml, water 295 ml, starch solution 5 ml. Place the conical flask in a water bath maintained at a room temperature and stir the solution well. Now take another flask labeled B, and to that we are adding thio 10 ml, potassium iodide 10 ml, water 80 ml, so that the total volume is 100 ml. Place that flask also in a water bath maintained at room temperature and mix the solutions by stirring. Now, a third conical flask labeled C, to that we are taking thio 10 ml, but potassium iodide 20 ml, water 70 ml. Again, total volume is the same. Now, stir the solution well. Now, another flask labeled D, to that we are taking thio 10 ml, potassium iodide 30 ml, water 60 ml. Again, the total volume is 100 ml. Now, mix the solution by stirring. So, in these three flasks, we take the same amount of thio, 10 ml, 10 ml. Also, the volume of solutions are the same, that is 100 ml. But in the case of potassium iodide, the amount increases 10 ml, 20 ml, and 30 ml. So, therefore, the concentration of thio remains the same, while the concentration of potassium iodide increases. Now, take another conical flask labeled E and place it in a water bath maintained at the room temperature, and to that we take 25 ml from flask A and 25 ml from flask B, and we need a stopwatch and a stirrer. Now we mix these two solutions and immediately start the stopwatch. So mix it, stir it, we started the stopwatch and we are waiting for the color change. When blue color appears, we immediately stop the stopwatch. 50 seconds, 54, 57, and a color appeared. Blue color appeared, we stop the stopwatch. So the time is 1 minute. Now we remove the solution and clean it, and to that now we add 25 ml from A and 25 ml from C, and as before we use a stopwatch. So we immediately start the stopwatch when we mix these two solutions, 25 ml from A, 25 ml from C. So the stopwatch is started. And the blue color appeared. So we stop the stopwatch and the time required is 30 seconds. Now we remove it, clean the flask, and to that now we take 25 ml from A and 25 ml from D, and immediately start the stopwatch. So we transfer the solution and we start the stopwatch, and we wait for the color appearing. So it is 18 seconds. We have tabulated the data that we obtained in the experiment. Composition of the system. In the first case, the 25 ml from flask A, 25 ml from flask B, and a volume of potassium at 10 ml. And a time to appear blue color is 60 seconds. And a second case, it is 25 ml from flask A plus 25 ml from flask C, and volume of Ki, the volume of Ki is 20 ml, and the time is 30 seconds. And for third one, 25 ml flask A plus 25 ml flask D, the volume of potassium iodide is 30 ml, but the time is 18 seconds. These values are arbitrary and not an actual experimental data. The two reactions taking place are, the first one is a slow reaction, that is oxidation of iodide ion by iodine peroxide, and the second one is a fast reaction, the reaction between thiosulphate and iodine giving tetrathionate ion, and therefore the rate of this reaction depends on the first step. We can plot a graph using the data we obtained. In the y-axis we plot volume of potassium iodide solution, and in the x-axis time. And the volume of potassium iodide solution is proportional to the concentration of potassium iodide. So at this point the concentration of potassium iodide is maximum, and as the reaction proceeds, the concentration of potassium iodide decreases. Initially the rate is high, that we can observe from the slope of the graph. If you plot a tangent and find the slope will be high, and compare it with this one. So here the slope is less. So that means the slope gives the rate of the reaction, and we can say that the rate decreases as the reaction proceeds. We now discuss some multiple choice questions related to the topics that we have already discussed. That is the physical chemistry experiments. Question number 1. The calorimeter constant is option 1, heat absorbed by cold water, heat absorbed by the calorimeter, heat absorbed by thermometer and stirrer, heat absorbed by calorimeter, thermometer and stirrer. The calorimeter constant is the heat absorbed by all the three: calorimeter, thermometer and stirrer. So option 4 is the correct answer. Question number 2. Enthalpy changes are directly related to temperature changes by the relation option 1 delta H is equal to mCp delta T, option 2 delta H is equal to VdCp delta T, option 3 delta H is equal to mCv delta T, and option 4 both 1 and 2. And we know the relation between delta H and Cp is given as delta H is equal to mCp delta T, where m is the mass and Cp is the heat capacity at a constant pressure. So option 1 is the correct answer. But we can also choose option 2, because V into D, where D is the density and V is the volume, V into D is M. So we can replace M by V into D. So therefore both option 1 and 2 are correct. Question 3. The incorrect statement among the following is: 1. Heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. Heat capacity is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Heat capacity is the amount of energy required to raise the temperature of 1 mole of a substance by 1 Kelvin. Heat capacity of water is 4.184 joule per Kelvin. And in the definition of heat capacity, we use the quantity as 1 gram. The rise in temperature is 1 degree. So option 1 and 2 are correct. But option 3 is incorrect because we use 1 mole. And option 4 also is correct. The heat capacity of water is 4.184 joule per Kelvin. Hence, the incorrect statement is option 3. That is the correct answer. Question number 4. A student used a styrofoam cup as calorimeter. While determining the calorimeter constant, the following data were obtained. Volume of cold water equals 50 ml, temperature of cold water 25 degrees Celsius, volume of hot water 50 ml, temperature of hot water 70 degrees Celsius. The maximum temperature attained is 45 degrees Celsius. The calorimeter constant will be option 1 45 joule per Kelvin, option 2 60.5 joule per Kelvin, option 3 103.5 joule per Kelvin, option 4 52.3 joule per Kelvin. Since this question is a numerical one, we have to find the answer by calculation. So we know that the calorimeter constant is given by the equation W equals minus 4.184 into mH into Tm minus Th plus Mc into Tm minus Tc divided by Tm minus Tc. And mH is the mass of the hot water and Mc is the mass of cold water and Tm is the temperature of maximum temperature, Th is the temperature of hot water, Tc is the temperature of cold water. So substituting these quantities and upon simplification we get the answer as 52.3 joule per Kelvin. So option 4 should be the correct answer. Question number 5. It is an assertion reason question. Assertion. When anhydrous copper sulphate dissolves in water, heat will be liberated, while hydrated copper sulphate dissolves in water, heat is absorbed. Anhydrous copper sulphate does not contain water crystallization, but hydrated copper sulphate contain water crystallization. Option 1, both assertion and reason are correct, and the reason is the correct explanation for the assertion. Option 2, both assertion and reason are correct, but reason is not the correct explanation for the assertion. 3, both assertion and reason are correct. 4, assertion is correct, but reason is incorrect. We have already studied that when an ionic compound dissolves in water, the ions leave the ordered position on the crystal lattice and become free. Energy is needed for this process and it is taken from the surroundings. So the process is endothermic. And this happens generally with compounds which do not form hydrates and hydrated salts. But when an anhydrous salt dissolves in water, hydration occurs, which is an exothermic process and releases more energy than that needed to dissolve the salt. Hence the process is exothermic. So therefore the answer should be option 2, that is both assertion and reason are correct. But reason is not the correct explanation for assertion. So reason here is anhydrous copper sulphate does not contain water crystallization, but hydrated copper sulphate contain water crystallization. The statement is true, but it does not explain clearly the assertion. Question number 6. Which of the following compounds will show negative enthalpy of solution when dissolved in water? KCl, copper sulphate 5:0, copper sulphate, sodium nitrate. We know generally salts that do not form hydrates and hydrated salts show positive enthalpy of solution. For anhydrous salts, the enthalpy of solution is negative. And here KCl and NaNO3 do not form hydrates, so they must show positive enthalpy of solution. Copper sulphate 5:0 is hydrated, so that also shows positive enthalpy of solution. And option 3 is anhydrous copper sulphate, so that should show negative enthalpy of solution. So the correct answer should be option 3. Question 7. Assertion: the solubility of most ionic compounds in water increases with the rise of temperature. Reason: for most of the ionic compounds, enthalpy of solution is positive and the dissociation process is endothermic. Option 1, both assertion and reason are correct, and reason is the correct explanation of the assertion. 2, 3 and 4. Here the assertion is correct. The solubility of most ionic compounds in water increases with the rise of temperature. And this is because for most ionic compounds the enthalpy of solution is positive and the dissociation process is endothermic. So when temperature increases, the dissolution increases. So option 1 should be the correct answer. Question number 8. Student A was measuring the enthalpy of solution of anhydrous copper sulphate and a student B was measuring the enthalpy of solution of hydrated copper sulphate using the same amount of copper sulphate and water used by student A. Which of the following will be correct? 1. Enthalpy of solution found by both A and B will be the same. Enthalpy of solution obtained by A will be positive. Enthalpy of solution obtained by B will be negative. Enthalpy of solution obtained by A will be negative. For anhydrous copper sulphate, enthalpy of solution will be negative. And since student A is using anhydrous copper sulphate, and the enthalpy of solution measured by student A should be negative. So the correct answer should be option 4. Question number 9. Increase of temperature will, option 1, increase the solubility of potassium nitrate in water, increase the solubility of copper sulphate in water, decrease the solubility of potassium nitrate in water, decrease the solubility of copper sulphate 5:2 in water. We know salts that do not form hydrates and hydrated salts show positive enthalpy of solution. For anhydrous salts, enthalpy of solution is negative. And we know for potassium nitrate and copper sulphate 5:2, the enthalpy of solution should be positive. And for anhydrous copper sulphate, it should be negative. So therefore, increase in temperature will increase the solubility of potassium nitrate in water since the process is endothermic. So option 1 is the correct answer. Question number 10. Assertion: the enthalpy of neutralization of a strong acid against strong base is always a constant. Reason: enthalpy of neutralization depends on the quantity of acid and base taken. Option 1, option 2, option 3 and option 4. Enthalpy of neutralization is the amount of heat liberated when 1 mole of H plus ions furnished by acid combines with 1 mole of OH minus ions furnished by base to form 1 mole of water. It is found to be 57 kilojoules per mole. This happens in the case of neutralization of a strong acid against a strong base. But when the acid, base or both are weak, some amount of energy is utilized for ionization of the weak acid or base. So the heat liberated will be less than 57 kilojoules per mole. Therefore the assertion is correct. And for a strong acid, strong base neutralization, enthalpy of neutralization is a constant. But the reason is wrong. Enthalpy of neutralization depends on the quantity of acid and base taken. But the reason given is wrong. That is, enthalpy of neutralization depends on quantity of acid and base taken. But we define enthalpy of neutralization for 1 mole. So therefore it is independent of the quantity taken. So the correct answer should be assertion is correct and the reason is incorrect. Question number 11. 50 ml 1 molar H2SO4 is completely neutralized by 50 ml 1 molar calcium hydroxide. The enthalpy of neutralization will be option 1 57 kilojoules per mole, option 2 minus 57 kilojoules per mole, option 3 minus 53 kilojoule per mole, option 4 53 kilojoule per mole. Sulfuric acid is a strong acid and calcium hydroxide is a strong base. The enthalpy of neutralization should be 57 kilojoules per mole. And since delta H is negative, the correct answer should be minus 57 kilojoules per mole. Question number 12. 100 ml 1 molar acetic acid is completely neutralized by 100 ml 1 molar sodium hydroxide solution. The enthalpy of neutralization will be option 1 minus 57 kilojoules per mole, option 2 less than 57 kilojoules per mole, option 3 higher than 57 kilojoules per mole, option 4 cannot be determined. Since acetic acid is a weak acid, some heat is required to dissociate the acetic acid. Hence the heat liberated will be lower. So therefore the correct answer should be option 2 less than 57 kilojoules per mole. That is the correct answer. Question number 13. Which of the following forms a hydrophilic salt? 1 starch, 2 egg albumin, 3 gum, 4 all the above. Hydrophilic salt means a salt water loving. Hydrophilic salt means water loving or solvent loving. All the three forms such salt. So the correct answer is all the above. Question number 14. Which of the following forms a lyophobic salt? 1 freshly prepared ferric hydroxide, freshly prepared aluminum hydroxide, arsenic sulphate, and option 4 all the above. A lyophobic salt means solvent heating, and all these three are lyophobic. So therefore the correct answer should be all the above. Question number 15. Statement 1. Lyophilic salts are more stable than lyophobic salts. Statement 2. In lyophilic salts, particles of dispersed phase have an affinity for particles of dispersion medium. Option 1, option 2, option 3, and option 4. The statement 1 is true. Lyophilic salts are more stable than lyophobic salts. And the reason is, in lyophilic salt, particles of dispersed phase have an affinity for particles of dispersion medium. So statement 2 is correct. And it is the correct explanation for statement 1. So option 1 is the correct answer. Question number 16. The stability of lyophobic salt is 1. Due to the charge on the colloidal particle. The charge prevents coagulation. Because of charge, colloidal particle remains suspended in the medium. And 4. All the above. The stability of lyophobic salt is due to all these three factors. Therefore, the correct answer is option 4. Question number 17. For a hypothetical reaction A plus 2B giving half C, the expression for the average rate could be written as 1. Rate is equal to delta A by delta T. Rate is equal to minus 1 by 2 delta C by delta T. Option 3. Rate is equal to minus half into delta B by delta T. And option 4. All the above. The rate of the reaction could be written as minus delta A by delta T, which is equal to minus 1 by 2 delta B by delta T, and that should be equal to 2 into delta C by delta T. So here since A and B are reactants, the rate expression should be negative. So the correct option should be option 3. That is, rate is equal to minus half into delta B by delta T. Here it is not given as negative, and for this one it should be 2 into delta C by delta T. Which of the following statement is not correct about order of a reaction? 1. The order of a reaction can be 0. The order of a reaction can be fractional. It is an experimentally determined quantity. Order is always equal to the sum of the stoichiometric coefficients of the reaction. We know order of a reaction can be 0 and it can be a fractional quantity, and also order is an experimentally determined quantity. So option 1, 2 and 3 are correct for the order of a reaction. But fourth one, order is always equal to the sum of the stoichiometric coefficients of the reaction, and that is not correct. But if the reaction is an elementary reaction, it can be the sum of the stoichiometric coefficients. So therefore, this statement is not correct. That means we are using the term always equals. So the correct answer should be the fourth option. Question number 19. Which of the following statement is correct? 1. The rate of a reaction decreases with the passage of time as the concentration of the reactant decreases. The rate of a reaction is same at any time during the reaction. The rate of a reaction is independent of temperature change. The rate of a reaction decreases with increase in concentration of reactant or reactants. We know the rate of a reaction decreases with the passage of time as the concentration of the reactant decreases. So the statement 1 should be, option 1 should be a correct statement. And the second one, the rate of a reaction is same at any time during the reaction. And this is not a correct statement, and this is applicable only for zero order reactions. The rate of a reaction is independent of temperature, and that also is a wrong statement. The rate of a reaction decreases with increase in concentration of reactant or reactants, and this also is a wrong statement. The rate actually increases with the increase in concentration of reactants. The correct answer should be option 1. Question 20. Which of the following expression is correct for the rate of the reaction given below? It is an ionic equation, 2I minus plus hydrogen peroxide in presence of acid, it gives iodine plus water. Option 1, the rate expression delta I minus by delta T is equal to delta H plus by delta T. Option 2, option 3 and option 4. So the rate of this reaction could be written as rate is equal to minus half, since it is 2I minus half into delta I minus by delta T, and that should be equal to delta is 2O2 by delta T, since the stoichiometric coefficient is 1. Then H plus, it is minus half into delta H by delta T, and delta I2 by delta T, and a half into delta H2 by delta T. So here the expressions given are option 1, option 2, etc. So the correct relation should be, that means I minus and H plus. So therefore minus half into delta I minus by delta T should be equal to minus half into delta H plus by delta T. So therefore the correct answer should be option 1. Question number 21. Which of the following is correct expression for rate of reaction given below? Iodine plus thiosulfate giving the tetrathionate ion plus I minus. Option 1, rate is equal to K into concentration of iodine into concentration of thiosulfate. Option 2, K into concentration of iodine into 2 into S2O3. 3 and 4. These are the rate law expressions for the reaction, and iodine and 2 moles of H2O3 is there. So the correct option should be the fourth one, that is K, rate is equal to K into concentration of iodine into concentration of thiosulfate raised to 2. That is the correct answer. Question number 22. The rate of the following reaction is found to be doubled when the concentration of iodine is doubled, keeping the concentration of thiosulfate constant. The order of the reaction with respect to iodine will be. This is the reaction. Option 1, first order. Option 2, second order. Option 3, zero order. Option 4, pseudo first order. Since the rate of the reaction is doubled when the concentration of iodine is doubled, the rate is directly proportional to concentration of iodine. So the reaction should be first order with respect to iodine. That is the correct answer. Question number 23. Rate law for the reaction A plus 2B giving C is found to be rate is equal to K into concentration of A into concentration of B. Concentration of reactant B is doubled, keeping the concentration of A constant. The value of rate constant will be doubled, same, quadrupled, and halved. The rate depends on concentration of the reactants, but the rate constant is independent of the concentration. So therefore the answer should be option 2. Question number 24. In carrying out the iodine clock reaction, the concentration of thiosulfate used should always be less than the concentration of iodide ions. Reason: no blue color with the starch will be observed. Option 1, option 2, option 3, and option 4. When thiosulfate is present in excess, all the iodide will be reduced to iodine. There will not be any iodide ion and no I3 minus will be formed. Only I3 minus ion can form complex with starch, which shows the blue color. So therefore, the assertion is correct. And reason also is correct. And reason clearly explain the assertion. No blue color will be observed. So the answer should be option 1. Question 25. Starch shows a blue color with potassium and iodine solution. This is due to option 1, the presence of potassium iodide. Option 2, the presence of I2. Option 3, the presence of Ki3. Option 4, all the above. Starch forms a complex with I3 minus, which is blue in color. So the answer is option 3. Question number 26. Which of the following statement is incorrect? Option 1. The rate constant is the rate of the reaction when concentration of reactants is unity. Rate constant of a reaction is independent of concentration of reactants. For a zero-order reaction, rate will be a constant. Option 4. The rate constant is independent of temperature. So we have to choose the incorrect statement. For a hypothetical reaction A plus B giving products, the rate law could be written as rate is equal to K into concentration of A raised to X into concentration of B raised to Y. When the concentrations of A and B are unity, rate will be equal to K. That means the rate constant is the rate of the reaction when the concentration of reactants is unity. So it is a correct statement. Rate constant of a reaction is independent of concentration of reactants. Rate depends on concentration, but rate constant is independent of the concentration of reactants. So option 2 also is a correct statement. For a zero-order reaction, rate will be a constant. For a zero-order reaction, rate is independent of concentration. So rate is a constant. Hence, option 3 also is a correct statement. Now option 4, rate constant is independent of temperature, but rate constant depends on temperature. So option 4 is the answer. Question 27. Oxidation number of sulfur in tetrathionate S4O6 2 minus is option 1 plus 4, option 2 plus 6, option 3 plus 4 and plus 6, option 4 0 and plus 5. The tetrathionate ion is this one. The central sulfur atoms are assigned an oxidation number of 0 and the other two plus 5 each. So the correct answer is option 4, 0 and plus 5. Question 28. Match items in column 1 with that in column 2. Column 1, mathematical expression for rate of the reaction, rate of zero order reaction, unit of rate constant. For a complex reaction, order depends on. Column 2, slowest step, rate law, etc. Option 1, option 2, option 3 and option 4. Mathematical expression for rate of the reaction, and that is the rate law. So A in column 1 could be connected to 2 in column 2, that is rate law. B, the rate of a zero order reaction, and a rate for a zero order reaction, the rate is same as the rate constant. So B to 3. Unit of rate constant for a zero order reaction, that is mole per liter per second. For a complex reaction, order depends on the slowest step. Therefore, the correct option should be A to 2, B to 3, C to 4 and D to 1. That is option 3. Question number 29. The reaction between potassium iodide and hydrogen peroxide in presence of sodium thiosulfate in acid medium is called cloak reaction because 1. It is a cyclic reaction. 2. For doing the reaction a cloak is needed. It is a periodically repeating reaction. The reaction is kinetically followed by noting the time needed for color change. So it is called a cloak reaction because the reaction is followed by the time needed for the color change. So option 4 is the correct answer. Question number 30. Sulfur precipitated from thiosulfate according to the reaction thiosulfate plus H plus giving water plus sulfur dioxide plus sulfur. The rate law for the reaction can be written as rate is equal to K into concentration of H2O3 2 minus into concentration of H plus raised to 2. How many times the rate will increase if the concentration of both thiosulfate and H plus are doubled? Option 1 2 times, 8 times, remains constant, and option 4 4 times. The rate law for the reaction is given. So we can say the rate before doubling, that is R1 equal K into thiosulfate into concentration H plus raised to 2, and let it be equation 1. And now we double the concentration of both. So then there should be a change in the rate, and the new rate could be written as X into R1. So that is K into 2 into S2O3 2 minus into 2H plus raised to 2. X into R1 equals K into 2 S2O3 2 minus into 2H plus raised to 2. And we get equation 2. Now we divide equation 2 by 1. We get X as 8. So the rate will increase 8 times.